Okay, welcome to the Digital Transformation for the Steel Industry webinar. Today we have the great pleasure to listen to Burke Birand, Chief Executive Officer at Fero Labs, and also Jenna Kreutzer, a process engineer, and Brian Williams, metallurgist from Gerdau, Cartersville. The title of the presentation today is Accelerating Product Chemistry Refinement Using Explainable Machine Learning. Before we start the webinar today, I want to go through some important reminders to the attendees. Please note that the attendees' audio has been disabled. Any questions to the presenters should be submitted via the chat feature. The host and the moderator will determine which questions are presented to the presenters. And please do also be aware that this session is being recorded and will be available for on-demand replay on AIST's website. If you experience any technical difficulties, please contact training@aist.org. Please note that photos and recordings of presentations are prohibited. We will be giving a link to access presenter-approved presentations and recordings following the end of the webinar. Due to the large size of these files, please allow 2 to 3 workdays before they will be available online. If you have noted that some of the previous webinars are not available, this is because we are still waiting for presenter approval. I would also like to brief you on AIST antitrust guidelines, which emphasizes the antitrust law that prohibits agreements between individuals to regulate prices and to hinder or limit a competitor. I would also like to brief you on AIST anti-harassment policy, which emphasizes the importance to provide a harassment-free environment regardless of age, race, disability, or gender. Okay, so I would hereby like to present the sponsor for the event today, Fero Labs. Fero Labs develops an industrial process optimization software that uses cutting-edge machine learning to optimize factory production. Their software enables process engineers to build ML models to predict quality issues and identify production bottlenecks. In addition to predictions, their tool provides valuable insights and root cause explanations to build trust. And Fero Labs' focus sectors include metals, chemicals, energy, and automotive. And they count as customers of some of the largest industry companies in the world, including Gerdau, Henkel, Covestro, and Volvo Trucks. So thank you very much to the sponsor of this event today. I would hereby like to introduce to you the moderator of the webinar, Ramesh Kajayam, Consulting Systems Engineer at Prime Metals. Kajayam obtained his Bachelor's of Technology in Electrical and Electronics Engineering from Nagarjuna University in India in 2003, and a master's degree in Electrical Engineering from West Virginia University in 2006. He worked for Siemens for 2006 and 2015 and has since been working for Prime Metals Technologies. Kajayam is a licensed professional engineer in electrical engineering. He is an active volunteer of IEE Industry Application Society's Atlanta chapter, and he previously served as the papers chair and currently as the chair for the AIST Electrical Applications Technology Committee. Kajayam has presented technical papers at both IEE conference and at AIST. His current interest is in digital applications in the steel industry with a focus on electrical systems. So I would hereby like to give the word to the moderator of the event, Ramesh Kajayam.
Thank you, Alicia, for that. And I would like to actually introduce our presenters today. I have the pleasure to introduce the 3 best personnel in the steel industry right now. The first is Burke Birand. Bert Byron is the co-founder and chief executive officer of Fero Labs, a machine learning software company focusing on industrial process optimization. He has been working closely with steel manufacturers since 2015 to bring cutting-edge explainable machine learning models to the factory floor. Bert is a seasoned speaker, having given keynotes at various industry conferences around artificial intelligence, machine learning, as well as being featured as a TEDx speaker. He holds a PhD in electrical engineering and computer science from Columbia University, where his academic research focused on Internet of Things, systems for enterprise-grade resilient networks. Our next speaker is going to be Jana Cruiser. Oh, that's a fantastic photo, right? Jana Cruiser is a process engineer in Gerdau's technology group. She joined Gerdau after college and completed their management associate program and has worked in melt shop process improvements for the Knoxville and Cartersville steel mills. Currently, she focuses horizontally across all Gerdau mills with systems integration to ensure the best cost decisions from a process and technology view. She holds a BS degree in mechanical engineering from South Dakota School of Mines and Technology and is working on completing her MBA at Ashford University. We wish her the best. Last but not least, our final speaker is Brian Williams. Brian Williams is a metallurgist at Gerdau Long Steel North America Cartersville Mill. He joined Gerdau in 2014. Prior to Gerdau, he was the quality manager and plant metallurgist at a commercial heat treatment facility in Rockford, Illinois, USA, primarily serving the automotive and aerospace industry. He is currently responsible for providing quality support for rolling operations within Cartersville. He holds a BS degree in metallurgical technology from Arkansas State University, as well as certified lead nuclear auditor. So with pleasure, and also I want to thank Fero Labs that we do have a new collaboration between Primetals and Fero Labs that is coming up new. So I wish you best to all three others. It's all yours. Thank you.
Thank you, Ramesh, for the wonderful introduction. And thank you, everyone, for joining this webinar. There's clearly a lot of talk around digitization, AI, ML, and with that comes a lot of hype and a lot of overblown expectations. And our goal with this presentation is really to clear some of this hype by sharing some very concrete learnings on a very specific use case that has already achieved substantial impact within Gerdau. As an agenda, what we'd like to do is first start by introducing the problem and then specifically go into more details about the actual results that Gerdau has achieved. And it's great to have Jenna and Brian on the line who will share these results. And then there's also lots of lessons learned in terms of deploying and scaling machine learning. So after this section, I'll go into more of this AI hype and clearing up some of the AI hype and specifically talking about how our technology, specifically explainable machine learning, has been helpful in achieving these results and scaling these results within Gerdau. So with that, I'll pass it on to Jenna.
Thank you. This morning, I'm here to talk about the business challenges that really drove us towards this project. The first one was the need to reduce raw input material costs while delivering quality. And this is a really reoccurring pattern in the industry. How do we continuously balance cost savings with our quality demands and ensuring that we maintain those quality demands? And the other one was, how do we get widespread adoption of tools so we can maximize the benefits across plants and have more of a horizontal focus instead of a very individual focus? Both of these main goals have really been heightened or emphasized by the COVID pandemic. COVID has really stressed our quality demands. We're running a lean process and we have much more limited room for error. And at the same time, it has put on this need for remote working capabilities. And we've been able, we'll discuss this a little bit later, but we've even been able to set up and start mills virtually without having an on-site business. So we've been able to maintain or achieve this remote work structure that's been demanded with COVID. With that being said, I'm going to pass it on to Brian, who will talk about the technical challenges.
Hello. All right. So, as Jenna well stated, even though we have to juggle these apparent business challenges, we also have to remain aware of the current technical challenges that we face, and also how to effectively manage those pros and cons of the current analytical methods that are out there for us. So, as we all know, we are familiar with traditional tools that are used, but those tools do have some limitations attached to them. Some of them have issues when we're trying to look at and evaluate multiple non-linear relationships. And it's also difficult to make real-time adjustments using some of those tools. And some of the other things that we have issues with is that the integration of some of those new tools and the workflow is not always a straightforward process. So if we're trying to tailor some of those tools to really look at details that affect our melting, casting, and also some rolling operations, sometimes we run into hiccups that can cause a delay in making necessary adjustments in order to salvage production in process. So if you can, Bert, can go to the next slide. Okay, so like I mentioned earlier, some of the traditional methods, as you guys are familiar with, are linear regression models, also some histograms, scatter plots and things like that. Those are very, very useful tools, especially when we're doing yield strength and calculating ultimate tensile and different things like that, and just looking at patterns, right? Being able to say, okay, now we're trending to get out of control or process control. And we want to make sure, those are good tools. We use those. They help us to stay on track. However, we're very limited in being able to make adjustments during process. And that was really the whole goal of adding machine learning to our process, was to be able to make adaptive decisions without much interference or with much delay. Because especially having scrap as our major commodity, we get variations every day throughout it, heat to heat. And so being able to make those decisions that also are cost-effective decisions, we needed this ability. Some of the other drawbacks there, as you guys are familiar with the traditional models, sometimes there's low accuracy when it comes to predicting mechanical results. We also have a very limited ability to be adaptive or to operate in real time. So if you can go to the next slide. Yep. All right. So now we talk about a little bit how machine learning helps us to alleviate some of those issues that we face using traditional models. Here we have two different silos that we decided to break up the workflow into. And so you have a static workflow, and then you also have a real-time workflow. The static workflow, for the most part, allows us to be able to conduct root cause analysis and then to better plan. So we can use the data that we have there to go back and say, okay, we're trying to design a new chemistry for a product that is being produced. And so we can go here and say, okay, now we know these parameters from production are very key, and they can help us make decisions whether if these inputs that we are adding into this silo are going to be helpful. Do they increase our accuracy or our chance of producing a successful chemistry on the first time, or do we need to go back and readjust some of our data inputs or take some away, just to improve that accuracy? So it gives us that ability. We also utilize heavily metallurgical knowledge, so it's one of those tools where you cannot separate the metallurgist from the tool. You have to work hand in hand. So especially when you're building newer chemistries, all of that data there, it's new for the first time, so that the system can't really process it as fast as you'd like it to, or as accurately. So you still need the metallurgist there to say, okay, hey, maybe there's something going on with your microstructure, or maybe there's something going on that we're not capturing in our data. And so it helps us to decipher that. That information also, those production parameters are also stored in real time. So we can take information that we've learned from the historical standpoint, as well as things that are going on currently. So if we want to look at it from, say, hey, we know how this product has rolled in the past, and some of the parameters that went into that, as far as temperatures, times associated with that, how would that behave if we were to change the chemistries? And so that allows us to be able to go in, make manual adjustments if need be, or we can do it in processing. So if we have samples currently in our chemistry lab, and as the test results are populated, those data points are then sent over to this silo, analyzed, and then an output is given back to us. And it populates itself in a certain range, so we know that, hey, we're good to go, or no, we need further adjustments to be made. So this just allows us that dynamic viewpoint of our process from the systematic standpoint, and then helps us to make better decisions that also help drive down some of the costs associated with production. If you can go to the next slide there. Okay. So in this slide here, we really broke down how we use machine learning in real time to help us with our live predictions and the modeling, and also how it works back to our operations floor. So this is more of an integrated layout here, where we have this silo for the real-time machine learning silo here, takes the data, and like we talked about earlier, we have a sample that comes into the laboratory. Those samples are tested, those results are put into that silo. That data point is gone then to the Fero cloud, there where that information is analyzed as compared to historical data points, and then an output is received. And that lets us know to say, hey, maybe we need to add XYZ components to, or such and such alloys to really help us reach our goal or our ultimate yield and tensile results. So if you can go to the next slide. Okay. And this here is an example of what those outputs may look like. So the test results are there, the chemistry is submitted. What we have set our system up to do is to look at historical production data from rolling. So we want to make sure that our operators have a viewpoint of, okay, your chemistries affect our rolling process, and the factors that are taken out of the rolling, such as temperatures, times, different things like that, deformation, all of that information is then fed into the system and paired with the chemistry. And based on whatever product is being produced, or a family, like size, like beams or channels or things like that, that information is generated and it gives you an output. And so in this example, that's why we have the tensile strength, and it gives you a range where those bars there gives you your set point for the your upper limits and your lower limits. And then you have your indicator there, and that indicator can be color coded. In our case, it is to let us know that, hey, we're within acceptable range, or where we'd like to be. And if it's out, if it's yellow or if it's red, it lets us know that we still need further adjustments to be done to our chemistry in order to ensure that we're going to be able to make the desired mechanical properties. So if you can, we can go to the next. And this is just a quick outlook of what we really have here. So it takes a little bit of where our operator will be able to see this in the pool pits in real time. So as they generate, their chemical results are populated. About a few seconds later, they'll have their estimated tensile result based on those chemistries. And so that's just what the operator sees. Like I said, it brings them back into the fold, be able to see what's going on from the high level, and then also be able to make real-time decisions, and they can communicate that with the other melt shop personnel or production personnel. So if you can also go to the next slide there. Okay, so metallurgical planning. As we all know, this could be some of the most taxing, especially if you have a new product coming online. This is one of the parts that really helps us the most, because we have the ability to make manual adjustments. We can go in and seemingly test out different ideas or methods. So if we want to say, hey, if we're making this beam, we want to use a relative chemistry that we've known, we can actually go in and make those adjustments and see what type of estimation we can get. So we'll know, okay, if we make an addition for chrome, if we do that, what did our ultimate tensile strength may come into? If we reduce carbon, you know, how that would play a part. But then we also pair that with metallurgical knowledge, because we also want to make sure that we're maintaining a fairly good microstructure, a clean microstructure, that we're not inducing any other abnormalities or anything like that that the system may not be able to pick up at the time. And so with having that ability, it really does allow us to better optimize grades, have a better prediction going into trials, especially with being in a production environment. Every trial costs money. And so being able to save some of those funds and alleviate having mishaps, I think that greatly helps us. And by having this planning stage there, it gives us that viewpoint. So, all right. And here is just a system, the way the system is designed here, and how we decided to deploy machine learning here. So at Gerdau, we do have our historians, IBAs. You have inputs also from the process. And all those are gone up into the network. From our network, we share that with Fero Lab in their cloud. And then they generate an output. And that output is gone to our workstations. And then also the information that they receive from those workstations goes back to the cloud, and it's stored there. So we can also make these adjustments. We have a running history of what we've done in the past, and then how it can affect us going forward. So that was just a very high level overview of how we have it set up and how we deployed machine learning here at Gerdau. So with that, I will pass it over to Burke. Oh, to Jenna, I'm sorry there.
Hi guys, so Brian explained kind of the technical side of the tool and how we use it in our operations. I'm here to review the business results seen by applying this tool in our operation. So one of the main benefits is we actually found the ability to make 30 grade changes, and I would say these are static changes. So we're actually moving the entire chemistry specification range. And when we've been able to do that, we've been able to achieve an average of 9% reduction on alloy consumption. In addition, the live prediction that Brian mentioned that's currently being deployed, it empowers operators to achieve savings by reducing alloy additions while staying within specifications. So the idea here is, you know, if the operator gets his first chemistry and he's low, he knows he needs to add. He gets his second one, it's all green, he's good, he can stop. And it kind of breaks down some of the barriers because he knows exactly, we can connect the dots. He knows what his tests are going to be. And instead of relying on chemistry, he's relying on the quality mechanical specifications we need, and he can just stop adding right there. So there's kind of two sides, the static benefits and the live optimization benefits that we're realizing. And it's important to know that both of these can be achieved because of the prediction accuracy of the model. So the median prediction accuracy of the model is within like 1,000, 1,100 PSI for both tensile and yield strength. And so it's very good accuracy. And in addition, because we know the prediction accuracy, we can take those boundaries and actually include them into our process and our analysis. So if we know there's a plus or minus 1,000 prediction, we can take our bottom and our top limits and build that in and have aims that have that prediction error already built in for operators. And that's kind of how we've been able to use it when we apply it onto the floor. In addition, these achievements are quantified on a monthly basis and tracked automatically. So this is an example. It's skewed to not show any of our product results, but every month we get a report that says, here's all your grades, here's the product, and then here's the alloy savings seen with these different alloys. And it really reduces the workload on the process engineer to have to go in and pull reports and analyze that aspect of the savings every month. It's just automated, and we get it right away. We can move on to the next slide, please. Okay, so there's additional results that we've been able to see. One is reduction of off-spec material. And this can be seen in two different ways. One, with that live or real-time model that Brian reviewed, it can help operators stay within the required specifications. So we kind of see that prediction, and he can hopefully build his heat to be within those ranges at all the time. The second is if something happens and he can't do that, our metallurgists can use the static model to help to predict, see, effects if the material needs to be regraded. So if that is not going to work for that intended purpose, can we go analyze 4 or 5 different options and figure out what would be the best option to put this material at? In addition, we've been able to achieve greater process stability in 2 ways. The first is data quality, and the model can help us highlight, if a particular variable is missing points often. So we can say like, our automation's lacking here, and this is a reoccurring problem for the model. And it can also point out, when bad data is harming prediction accuracy. So if we see prediction accuracy drop, we can go in and kind of look at our data quality and see if there's any issues. Second, in regards to process stability, we've been able to see product capability improvements. You can see an example in the picture to the left where we've been able to reduce the variability of a particular product. And in addition to that, we've been able to achieve what we would call our ideal mechanical properties performance. So depending on the grade, sometimes, we might have been very nearing our maximum limit, and we've been able to drop not only the variability, but the average to be kind of within an ideal medium range. With that, I already mentioned the automated reporting that helps reduce the workload of our engineers. And we've been able to see a faster product development cycle because a lot of these traditional analysis take tons of time to put together, and we've been able to automate that side. So now our engineers can really take more time analyzing and employing the results of that. And we can move on, please, Burke. Okay, so now we wanted to talk about scaling Fero across multiple mills. We've been able to make it operational in 4 mills this year. With more planned, and it's important that we state that the design at the beginning allowed us to expedite the rollout. So the last couple of rollouts only took a couple of weeks to really get an accurate prediction and model set up. When we're scaling to other mills, it's important to note that we're replicating the interface, but each mill is individualizing the data inputs and process parameters. Each mill may have access to different variables that they can include for analysis and see our prediction accuracy. And the recent results have shown good prediction accuracy across all the mills. And I think it's important to say, as we're scaling, because this is an integrated tool, we can also use this to compare processes horizontally and really learn from each other what is making our prediction stronger, what's impacting our process from mill to mill. With that, we can move on. So there are a couple of key lessons learned that we want to talk about, and we really wanted to spend some time here and focus in on this because these lessons learned help make that scaling ability there. Without these lessons, we wouldn't be able to scale at the ease we're seeing us being able to do right now. The first one is that our IT infrastructure is essential. So when we started to scale, the first mill we started to scale to, we had some issues connecting to the live data, like the way we set up. So it was very important for our IT to get involved and to help us connect data across multiple sources. And then data quality, we've mentioned this probably 2 or 3 times because it's very, very important. And one of the things that helps us determine how essential it is what are the requirements of data hygiene. So we had to really understand, our data flow, our storage, and our accessibility, also our formatting and how we wanted each variable to be presented, and as well as the relevant data points captured. So it's good to know that we can throw the model pretty much everything, and it will tell us if we gave it a variable that it's not finding impactful. It will leave it out of the prediction. So it's good to know that type of thing, and to see, like Brian said, compare it to our metallurgical knowledge. If that model left that data point out of the prediction, but we know it's a very important metallurgical data point that probably circles back to our data quality that we were talking about before, and it really gives us a better process understanding. When we deployed the machine learning impacts on data quality, we saw, skewed predictions. So if we have bad data, we're looking at something to see a really large confidence interval range that we're not used to seeing. And at the same time, we already mentioned that the software can flag when we're missing data points, and it can handle missing data points, which is kind of unique. And last, I want to talk about, and I'm going to spend a little bit of time here because it's very important, the change management in workflow. So Brian talked about how we're kind of dissociating old norms. Before, we were focused on a chemistry range and an aim, and now we're trying to add even more to that, and we're trying to tie it downstream to the final mechanical property results we're expecting to see. So not only does the operator need to manage his chemistries, he also needs to manage what the downstream effects of what he is doing. And so with that being said, it's very important that we spend time with that operator explaining what it does, how to use the tool, and the benefits from the tool. And we also need to allow time for that operator to really trust the model and the prediction and what it's doing. So there's that kind of change management. And then as we scale, we're getting into another change management type of conversation, which is more on the metallurgical side, which is like, how are all the different ways we can use this, and really expanding all the opportunity to expand the tools. So lots of important lessons here that helped us not only with the results of ours, but with the results of scaling. And I think it's important to note that one of the reasons why we were so successful is because this was built by the people who were going to be using it. So I think that's one of the things when we talk with Burke and Alp that really helped us have a success story here. It was driven and built by the people who are going to use it in the end. And with that, I'll pass it off to Burke, who's going to go into more of the AI hype discussion.
Thank you, Jenna. Yeah, so I'm going to discuss some of the points that around AI that's often heard in the industry, and starting with this result that only 35% of executives say that they are realizing value from AI investments. And this is kind of a stark number. And I think one of the main goals with this presentation is to discuss why Gerdau has been in that 35% of actually realizing value from AI investments and scaling and so forth. So I think one of the important things is that AI is always presented as kind of this magic bullet that's going to solve everything and just apply it, give it data and outcomes, business value. The reality is that there's a lot of hype, and most of these expectations are a result of hype. And there's different reasons for this. On the one side, there's notions about black box, AI being black box, which we'll get to, lack of trust in these models across the organization. And as a result of these, and a lot of over promises for sure. And the result of these is that AI actually, in most cases, actually does not deliver scalable results. So what is ML? And one of the things that we decided to do within Fero is that whenever we discuss AI, we'll kind of put it in quotes and use the term semi-sarcastically almost, and almost exclusively focus on machine learning. And really what machine learning is more powerful statistics, better math, essentially. But this definition actually kind of downplays the real value of ML because it's actually much more powerful statistics. ML allows us to identify very complex relationships in potentially large and messy data sets with missing values and that have unique kind of characteristics. But it also allows us to run live optimizations. And these are why ML methods are actually so much more powerful. Having said this, a lot of machine learning methods are actually not appropriate for industry. A lot of machine learning comes from companies like Netflix, from the tech sector, where the requirements are very, very different. Now, if you consider Netflix, a lot of these methods are black box methods. So Netflix operates many recommender systems. You give it some of your favorite movies, and it provides a movie suggestion that you're likely to watch. However, nobody really knows what's happening inside this box. Nobody really has to know why Netflix is suggesting a particular movie. Another example from computer vision, Google has many of these black box ML methods where you give it a picture and it tells you what's on the picture. And again, Google doesn't have to know or explain to you why it thinks there's a cat, what a cat looks like. And this is important because sometimes Google's methods are wrong. Sometimes they provide the wrong output. But in these cases, nothing bad happens. If Google predicts that this cat is a couch, nothing bad happens. There's no mission critical point result that this bad prediction causes. And in this case, this is okay. This is not an issue for Google. But there are other instances where this is an issue. Consider this is a recent event from June where Tesla on autonomous driving mode sees a truck that's overturned on the highway and essentially accelerates into the truck until at the last minute, the driver sees the truck and then hits the brakes. These are kind of similar methods, black box machine learning methods. And this is important. Luckily, this is not an accident that has caused any casualty. But the reason why this is happening is because when these models were trained, essentially, it was not trained with a truck overturned on the highway. And for good reason. This is a one-off situation that doesn't happen very often. But in this case, this is actually a problem that can be caused, and a problem that's essentially an overfitting problem. And this can happen in the steel world. This can happen by, let's say, one of your scrap heats having a particular chemistry that hasn't been seen before. And we still want our machine learning methods to react and deal with these predictions, deal with these situations in a good way. What we've done at Fero is essentially designed our entire core machine learning engine for industry. And what this means is that all of our methods that we use internally are explainable by nature. Effectively, Fero allows engineers to open up this box and see what's happening inside this box, so that the output is not just a prediction, but also a confidence in that prediction, as Brian mentioned, and then some explanations as to why the models are making these predictions. And these are very crucial requirements for a machine learning model to be used in industry. So I want to show some of the screens on what this means specifically for the industrial world. First, one of the big challenges is actually to build trust in these ML models. And what's really important here is for the engineers and to some degree the operators really understand when these models work well, the predictive accuracy that comes with these models, and also when they don't work well. And that's absolutely important. This is one of the screens from the Gerdau deployment, and there's many other screens similar to this that allows engineers to dig in and understand what the model is doing and when they can trust it and when they can't trust it. And these are some other examples of screens. First, all the models that we use identify the importance of different factors. And that's really crucial because it almost allows engineers to verify that the models have learned the right things by looking at the predictive accuracy of the important factors impacting tensile strength. They actually see relationships that they know about that are written in textbooks. And that's great because that allows the engineers to make sure that the models are learning the right things. And then there's always new insights that can be obtained from looking at these factor importance plots to understand, okay, why is this particular factor that we didn't think would have such a large impact is having a big impact on the prediction. And the second graph here also shows another important aspect, namely, what do these relationships look like? How can we, what is the effect of a particular chemistry or a particular process parameter? What does that impact look like based on historical data and based on what the model has learned? And really expose the shape of these relationships. Some of these are also well-known relationships that, again, a metallurgist can verify based on domain expertise, but others are new insights that can be obtained from just opening up this model, looking inside and seeing what it has learned. So I want to just finish with some final thoughts. We believe that industrial ML has different requirements than most other types of machine learning, and therefore industrial machine learning methods must be explainable and trustworthy. And this is really the goal here, is to generate value around a particular business case. And it's not just to do a proof of concept of trying out a new technology, but actually to deploy this and to use this in live and in real-time fashion. And these requirements are even more important when these models are deployed into live production. And another point that usually comes up is, there's a lot of hype and therefore there's a lot of skepticism about these methods. And that's actually good because it's actually up to the vendors and the machine learning developers to build trust in these models. And what we see is that essentially, if there's no results being shown on a particular use case of machine learning, then I think it's safe to assume that there weren't any meaningful results achieved through this application. Similarly, if this particular use case has not been scaled within an organization, then that's probably a one-off POC that didn't demonstrate value. Because if it did demonstrate value, then why would it not be scaled and used across the board the way Gerdau has done? The third point that Jenna also touched on is that process engineers should be the ones building the models and be involved in building these models. This is very important because it allows them to investigate other use cases. Maybe aside from the tensile strength use case, there's other applications for particular types of defects that are also important. And an engineer being able to run these analyses themselves based on their priorities and based on the priorities of the mill is actually very, very valuable. And this is why we think that this power has to be on the engineers front, similar to how Six Sigma has done with classical statistics. When classical statistics was being applied to the industrial sector, the approach was not, let's take a lot of statistics PhDs, put it in a room and have them develop machine or statistical methods to improve with production. The goal was, how can we teach these methods to the engineers that are dealing with these issues on a day-to-day basis? And this also directly creates more trust in the capability of the models and allows these to be scaled in a more trustworthy way. Another point that always comes up in a question that we get is the quantity of data. And what we like to say here is that it's not really about data quantity, but it's mostly about data quality. One of the goals of ML should be to actually extract more information from the data sources that are already available. So the goal is not to ingest terabytes and terabytes of data and be able to provide insights from these large quantities of data, but really to use the same data sets that are already being used and then extract more information from them. And just to illustrate this point, in many cases, let's say you have a particular batch of steel and you're measuring one particular temperature about this batch. The data size is very, very small. It's basically one number for that batch. But let's say we move to a world where we are storing and ingesting the temperature every 10 milliseconds throughout this batch. The data size now, it's almost 1 million times more, but there's not that 1 million times more information in that data. I would say there's more information, but not 1 million times more. And that's why we believe that machine learning methods should be powerful enough to extract more information from data that's already available. And then a decision can be made to collect more data and to advance the process control systems or sensor systems to collect more data. But ultimately, the goal is not to get as much data as possible, but rather to get good quality data and good data hygiene. And the last one is probably the most important here, is that digitization of team sport. It takes a village to have this deployment. And within Gerdau, beyond Jenna and Brian, there's been many, many people involved in helping build these use cases and deploy Fero across several mills. And ultimately, what we're discussing is our modern process optimization tools, and they must empower the domain experts to make better decisions. And it takes a lot of people to make this successful. So with that, I'll switch over to the Q&A. I think, Alicia, we have some questions maybe from the audience.
Okay, thank you, Burke. That was an excellent presentation by three of you. It was a good collaboration between the algorithms and the process, bringing the metallurgy and suggesting the mix. We do have some questions today. We'll start with the first question from Klaus Stahl. You talk about real-time machine learning. Is it correct that it actually is the real-time application of machine learned algorithms, or the actual learning is done offline?
Maybe I'll take this very quickly. I think the distinction is that the training is done offline, a few times a day or a few times a week, but the predictions and the optimizations are done in real time. So that the idea is that the predictions, the models are used on a very quick time scale, and then the models themselves adapt over time to predictions, to new data and new process data that's coming from the plant.
Okay, thank you. We have the second question from Marco Taibo. Does the AI also suggest the best charge considered scrap mix?
Okay, I'll take a stab at that there. So the short answer to that would be yes. The model does have the ability to take into consideration the incoming scrap. However, that's really up to the person who is implementing this or the company to base that off of your use case, and it can vary from mill to mill or, process to process. But yes, it does have the ability to do that. It can be included into any of your inputs that you'd like. So.
Okay, good. The third question is from Mr. Ronald O'Malley. Is the property prediction only chemistry based, or is there other processing conditions also that are taken into consideration?
Okay. Yes. So it is chemistry based. However, all of the other processing conditions are also taken into account. As many as we can find that we feel that are having a massive um, impact on our prediction analysis, we definitely consider it. Are we capturing all of them at the time? Probably not. But we do have the ability to, as we find it, as we see that there's been process changes made, we can adapt our system to take those into account, or to remove ones that we find that are not having as big of an impact as we originally thought. So we do have that versatility there.
Okay. So now that you said yes, versatility is there. So there was a follow-up question. Is if it is so, how can real-time melt shop chemistry adjustments correct changes downstream?
So that goes a little bit more into us while we were taking into consideration the historical patterns of our production, like for rolling. So in our case, what we'd like to do is each rolling is a little different, but if we can try to keep some things constant, whether it be our temperatures and different things like that, if we can better control some of those, then we can better have better accuracy with our chemistry adjustments being made. And so it does, like I said, it does give you the ability to pinpoint what items you really need to focus in on, and we can go from there.
Okay.
One of the things I'm going to elaborate onto what Brian says, some of our models use rolling temperatures, and this is a good question of how that can be done. So if we know our rolling temperatures are going to change, and that's a downstream adjustment, we can kind of simulate that in the model to see what kind of chemistry adjustments we need to make. That would be a specific example of how we would do that.
Correct. Yep.
Okay. All right. The next question from Marcelo Cardoso. Could the presenter elaborate on the machine learning or statistical algorithm used for developing the model?
Absolutely. So one of the key things that we're doing differently is choosing the right family of machine learning models. ML is a very large family that encompasses many different types of models. Most of the models that we use are Bayesian machine learning models. And this is research that's coming from the research of our chief scientist. And before that, that came actually through several DARPA grants, where the goal was to use a particular type of machine learning and understanding what the machine learning models are doing. So the short answer would be that these are Bayesian machine learning models. It was the technical name for it.
Okay, good. Next question is from Sri Shilan C. How much the process kinetics and the speed of simulation or prediction is comparable?
So I think we can try to answer this, and if we get it wrong, let us know in the chat box again, and we'll go back to you. But the prediction is within a minute or two. So as far as the process, if we're doing a prediction every time we take a chemistry sample, those have 5-10 minute gaps, and then we have a minute prediction after the sample is taken. So that's kind of the workflow speed of things. I hope that's what you're asking. Like I said, if we get it wrong, just retype down here and we'll try it again.
Yeah, Sri Shilan, so if that did not answer, just follow up with a question. Next question is from Bruno Veiga. How do you work with the manual composition correction in the ladle furnace?
Oh, are you mentioning, if you're suggesting, I guess, how we make the manual additions? So what we're trying to do is branch out and say, so if we have an alloy addition, what we can do is say, okay, the system can estimate how much more we need. So those are some of the things that we're looking into going forward. Hopefully that answers your question there.
I guess the question is the manual composition correction. I guess maybe. Okay, we'll move on to the next question from Allison. Did you confirm the influence of each process parameters on the mechanical properties? Are they according to the metallurgical knowledge? For example, how does CB influences the YS and TS? Those are, I guess, the short names for the compositions.
So I would say yes, and this is kind of seen in the factor graph that Burke went through. It walks through each factor's impact on the prediction, and for something like columbium, it will have a different impact level versus the yield strength and the tensile strength. So we'll compare that to, you know, Brian's metallurgical knowledge and really make sure they match. Sorry, I'm mispronouncing that word. But yeah, so we do walk through all of that. And if there's a question, you know, like I said, in the design phase, one of our predictions wasn't matching metallurgical knowledge. And that was a big pinpoint to us, this whole data quality lesson that we learned. So we did match, and when we found errors, we investigated those. We didn't just abandon the prediction. I think that was a very important step for us.
Okay. I guess we have time for a couple more questions. I'm going to continue. Specifically to the steelmaking process, what other applications are you looking into applying machine learning to?
Okay, so we have a lot of different applications. Burke can probably go into some more, but specifically for the focus on this tool, like we said, the more we use it, the more ideas we come into on how we can use it. So right now it's a prediction on yield and tensile. Brian actually showed you the optimization. So the next step is to optimize over what levels of manganese and columbium we can hit and still achieve our yield and tensile strengths. And we can optimize over alloys too. So then the next step would be how many alloys, as we saw in that picture, can we use? And there, in that step, it's pretty interesting because we get a cost component. So we optimize for cost and while maintaining the metallurgical. So that's the three next steps, or kind of the three phases we see for this specific tool. I know there's been other stuff, and I'll let Burke pass it off to on maybe some of the quality yield stuff and as well as the emission stuff.
Yeah, absolutely. So there's different targets that can be chosen beyond the mechanical properties. So one that we're actively investigating is the predictions on flange defects. Other similar examples have been, let's say, predicting and targeting, you know, mill scaling for other types of products. Another use case that's been also very important is predicting emissions and understanding the drivers of emissions and how we can control those to lower those emissions or estimate emission measurements before actual hardware measurements are taken.
Okay. I guess we'll take one more question. Have you ever thought how to integrate in the models the experience of the operators in order to improve the performance of the system?
Yes, so we have actually greatly thought about that. How do we pair the experience from those who see the production every day with also comparing that with the models? And that really is what drove us to actually have a output that's there in the labs for them. So it won't only be in our chemistry analysis lab, but we're also trying to bring it to the floor. So other pulpits there, so they get the real-time knowledge, so they'll be able to understand that and make better adjustments there, because we want to utilize that experience of the operators. And so right now that stage is still in its infancy, but as we go, we will definitely be able to make better changes and monitor how that is progressing throughout. So yeah.
Okay. Alicia, do you think we can? Okay, so we can ask one more question. Does the model consider cost of the alloy if there can be more than one way to adjust chemistry to get the desired result?
Yes, we can put that in there to evaluate the cost. So those are different avenues that we have been looking into. And so we won't divulge too much of, I guess, some of that that knowledge there, but yes, it is possible. So.
Okay, so what is the time savings to complete a development of an entire new product?
So with this one, it's very interesting, right? Because time can be rather objective. But what we can do is that we have a greater chance of making an accurate prediction the first time, especially if we have material that it's similar to other products that we've rolled. We can build that. But if we're making a brand new chemistry, what we can do is just, like I say, go to the manual model. We can make real-time adjustments and see if it gets us into a ballpark. If that information is matching to our our knowledge base, and based on our equipment and our process parameters, it really does speed up that time, and it gives us a greater confidence. So it really does alleviate the guessing game, more to say, and really helps you out. And so by the time we get that first mechanical result, then we know if the process is really helped us or not. But I think with this one is more objective, but we do see the savings. We've never really looked at how much time it's saving us. However, the level of stress it saves is pretty unmatched. So.
Okay, thanks, Brian. We do have a lot more questions, but with respect to time, we have to stop here. And there is a comment from Ronald O'Malley that it's nice job, guys. So I think it is truly a good presentation. With that, I'll hand over to Alicia.
Okay, thank you very much for a very informative presentation. I would like to inform you about upcoming webinars here at the AIST. So the next upcoming webinar here at the AIST is machine-specific steel mill hydraulics. It is scheduled for today in the afternoon at 1 to 2 p.m. And the speaker is Brad Jensen from Alloy Technology Solutions. The next upcoming digital transformation webinar is by Schneider Electric, scheduled on Wednesday, 29th of July, same time as today. And the title of their presentation is Integrated Autonomous Crane Systems. So please make sure to register for those webinars. I would also like to inform you about the upcoming Digital Transformation Forum for the steel industry, which is scheduled 15th to 17th of March in 2021 at the Omni William Penn Hotel in Pittsburgh, Pennsylvania. Currently, the call for abstracts are open and the deadline to submitting is 25th of September. To submit your abstract, please visit AIST.org and then go to Conference Expositions, Technology Training, Digital Transformation Forum, and then Abstract Submittal. I would hereby like to thank everyone for attending the webinar today, and we hope and look forward to seeing you at future events. Thank you very much.